Welcome to all of you. Now we discuss bacterial growth in a chemostat. What is chemostat? Chemostat is this type of model. Actually, this is a device for harvesting bacteria or microbes. Now we pump sterile nutrient at some fixed rate into into a growth chamber. And this is the growth chamber at some fixed rate into growth chamber where the bacteria are being cultivated. And outflow, this is outflow valve, outflow valve allows the growth medium to live at the same rate so that the volume of the culture remains constant. Because the chemical environment is static or at steady state, so it is called chemostat. Chemical environment is static, so its name chemostat. The fluid volume, concentration of nutrients, pH, bacteria density, and other parameters are all assumed to remain constant throughout the experiment. This is the picture diagram for chemostat where we harvesting bacteria or microbes. Bacterial chemostat have many applications such as pharmaceuticals, how bacteria respond to different antibiotics to produce of therapeutic proteins such as insulin for diabetes, manufacturing to produce ethanol, the fermentation of sugar by bacteria, food industry used in production of fermented foods like cheese, and research to collect data for mathematical model of growth of specific cells or organism. Here we assume the growth chamber is kept well steered and there are no special variations in concentration of nutrient or bacteria. We focus attention on a single growth limiting nutrient whose concentration will determine the rate of growth of culture. The growth rate K of bacteria depends on nutrient availability, that is K equal to K is a function of C, which is an increasing function of C. And nutrient depletion occurs continuously as a result of reproduction of bacteria. Here from Wikipedia, the picture of this, the inflow of phase sterile medium, flow rate control valve, this air opening, and inflow of sterile air, and this bacteria culture or microbe culture, steering apparatus, and this the gaseous headspace, and this outflow of media and microbial cells to collect vessels, outflow of this. This from Wikipedia, chemostat, this is a bioreactor to which the phase medium is continuously added while the culture liquid containing leftover nutrients, metabolic end products, and microorganisms is continuously removed at the same rate to keep the culture volume constant. Here, we mathematical model construct the mathematical model. For that, symbol of mathematical model, N is the bacterial population density, C is the nutrient concentration in growth chamber, C0 is the nutrient concentration in reservoir, capital Y that is equal to 1 by alpha, this yield constant, obviously positive constant, capital V, volume of the growth chamber, capital F, intake or output flow rate, and K depends on C, function of C, the production rate of bacteria, and D equal to F by V, the dilution rate, positive quantity. And due to mass conservation of bacteria and nutrient, we respectively get dNdt equals to Kc minus D into N, and dCdt equal to D into bracket C0 minus C minus alpha K into N. In equation 1, the dNdt gives the rate of change of bacteria, and second term of the right hand side, that is K into N, gives the reproduction of bacteria, and the third term, that is equal to minus Dn, gives the outflow of bacteria. So dNdt is the rate of change of bacteria, which is equal to the reproduction of bacteria and the outflow of bacteria. This. In the second equation 2, dCdt gives the rate of change of nutrient, and the first term of the right hand side, that is dC0, gives the replenishment of nutrient from reservoir, and second term is equal to minus dC is due to depletion for outflow of nutrient, and third term is minus alpha Kn is due to depletion during the growth of bacteria. If the initial value, that is N at the time 0 and C at the time 0 is given, then we find the solution for N and C of equation 1 and 2. And for equilibrium points, that is steady states, dNdt equal to 0 and dCdt equal to 0 at equilibrium star sister. So dNdt equal to 0 gives K sister minus D into N star equals to 0. Obviously, N star equal to 0 or K sister equal to D. Case 1, if N star equals to 0, then and dCdt at the point N star sister equals to 0 gives D C0 minus sister minus alpha K sister into 0, because N star is 0. So sister equal to C0. Thus, we get the equilibrium point is E0 is equals to 0, C0. This 0, 0, C0 is we call this washout equilibrium point. Here N is equal to 0. So washout condition, equilibrium point. If Kc, K sister equals to D, then we get dC0 minus sister minus alpha D into N star, because K sister equal to D and this N star. So we get N star equals to 1 by alpha bracket C0 minus sister. And thus a normal equilibrium point, this E star equal to N star sister, where N star is equal to 1 by alpha bracket C0 minus sister and K sister equal to D. Obviously, N star exists, that is feasible, if sister minus C0 minus sister is positive, physically meaningful, if N star is positive, that is if sister is less than C0, then K sister is less than Kc0, because Kc is an increasing function of C. Obviously, K sister equal to D, then D is less than Kc0. Thus, a necessary and sufficient condition for existence of normal equilibrium point in star system is that D is less than Kc0. Now, uh, we examine stability test for these equilibrium points. Let if a function of nc equals to kc minus d into n. Kc minus d into n, actually the right hand side of the equation 1. This is called f, function f, nc. And this called gnc, right hand side of equation 2. So f equal to this, g equal to this. Then partial derivative with respect to n, del f del n equals to k minus d, and del f del c equals to k dash into n. Del g del n equal to minus alpha kc, and del g del c equal to minus d minus alpha k dash into n. Then the Jacobian matrix for the system J, we get J equals to del f del n, del f del c, del g del n, del g del c. So kc minus d k dash n minus alpha k minus d alpha k dash into n. Now for equilibrium point E0, this is equal to 0, C0, put n equal to 0 and c equal to c0. Then the value of Jacobian J equals to kc0 minus d 0 minus alpha k c0 minus d. This put n equal to 0 here and c equal to c0. Since it is a lower triangular matrix, because this element is 0, so eigenvalues are k c0 minus d and minus d. Now, both of these will negative. Both of these will be negative if k0 minus d is negative and minus d is negative, obviously. Then E0 is locally asymptotically stable if kc0 less than d. Since here n equal to 0, because this equilibrium point is 0 equal to 0, c0, so here n equal to 0, the first coordinate will be 0. Bacteria will be eventually washed out if kc0 less than d. But in this case, normal equilibrium point star does not exist, because for existence of star, a necessary sufficient condition for the existence of normal equilibrium point star is this d is less than kc0. D is less than kc0, but here kc0 is less than d. So in this case, kc0 less than d, normal equilibrium point does not exist here. But when kc0 is less than d, the washout equilibrium point E0 is locally asymptotically stable. Next, for equilibrium point E star, normal equilibrium point N star and C star, when D is less than kc0, we get J equal to this and put D equal to kc star here. Since D equal to kc star, already we have this, and then we get this. So the characteristic equation of this matrix is this minus lambda in this minus lambda equal to 0. So this is the quadratic in lambda, that is lambda square into this lambda plus something equal to 0. By Raoult-Hurwitz criteria, as the coefficient of lambda and constant term are positive, this coefficient of lambda and the constant term is positive, the eigenvalues will be either real negative or real negative, that is real lambda is less than 0. Then the equilibrium star is locally asymptotically stable if this coefficient of lambda and this constant term are positive. So in this plane C0 and D axis, plot this. So we carve D equals to K C0, and if C0D lies above the curve D equal to K C0 in the C0D plane, then equilibrium point E0 exists and stable. And for any initial condition N0 C0, and C0D lies below the curve, this, then E star exists and stable for any N0 C0. When D is less than K0 in this region, below the curve D is less than Kc0, and for upper portion D is greater than Kc0. Next question, in University of Calcutta 2021. Consider the following model of bacterial growth in a chemostat dn dt equal to K1C by K2 plus C into N minus Fn by V, dCdt equal to minus alpha K1C K2C into N minus Fc by V plus Fcd by V, where symbols have their usual meanings. So that equations can be reduced to following dimensionless form by substitution: n equal to fk2 by alpha vk1 into u, c equal to k2v, and t equal to v by f into tau. And we get non-dimensional form of the given equation: du d tau equal to alpha 1 v by 1 plus v into u minus u. dv d tau equal to minus v by 1 plus v into u minus v plus alpha 2. Alpha and alpha 2 are parameters to be determined by u. And question B, find the equilibrium points of this dimensionless system. Find the conditions on alpha and alpha 2 so that the equilibrium points become biologically meaningful. Determine the stability of the biologically meaningful equilibrium points. Now we have the model, this equation 1 and equation 2. Here int is the bacterial population density, Ct is the nutrient concentration in growth chamber, and C0 is the nutrient concentration in reservoir, V is the volume of the growth chamber, F is intake or output flow rate, 1 by alpha is the yield constant, positive quantity, K1 maximum specific growth rate of bacteria, and K2 is the half saturation constant. Now we use the substitution in fk2 by alpha vk1u, c equal to k2v, t equal to v by f tau. Obviously, differential coefficient dn equals to fk2 alpha vk1 du, and dc equals to k2 into dv, and dt equals to v by f into d tau. So, equation 1, that is dn by dt. So, dn, we get dn equal to this, and dt equals to v by f d tau. So we get this, and after simplification we get du d tau equal to alpha 1 v by 1 plus v into u minus u. Obviously this alpha 1 equal to vk1 by f, vk1 by f. And equation 2, from 2, using the non-dimensional quantities 3, we get the equation 6, dv d tau equal to minus v by 1 plus v into u minus v plus alpha 2, where alpha 2 equal to f c0 by v, c0 by k2, alpha 2 equal to c0 by k2, c0 by k2, this is v. So after dividing both sides by f by v cancel, so c0 by k2 is alpha 2 equal to c0 by k2. Hence the non-dimensional form of the given system becomes equation 4 and 6, and alpha and alpha 2 given by 5 and 7. Now, equilibrium points, we must have du d tau equal to 0 equal to dv d tau. So, alpha 1 this equals to 0 and minus v by 1 plus v into u minus v alpha 2 equal to 0. From the first equation, obviously, either u equal to 0 or alpha 1 v by 1 plus v minus 1 equal to 0. That is either u equal to 0 or v equal to 1 by alpha 1 minus 1. When u equal to 0, from the second equation, put u equal to 0, we get v equal to alpha 2. And when v equal to 1 by alpha 1 minus 1, and from the second equation, we get v equal to this. So, minus u by alpha 1, u by alpha 1, because from v equal to 1 by alpha 1, so we get alpha 1 minus 1 equal to 1 by v. So alpha 1 equal to 1 by V, 1 plus 1 by V. So V by 1 plus V equal to 1 by alpha 1. And this, and so put V equal to 1 by minus alpha 1, and we get this equation. So we get U equal to alpha 1 into this. So we get the equilibrium points are E1 and E2. E1 is 0 alpha 2, E2 equal to U star V star, where U star is given by alpha 1 bracket alpha 2 minus 1 by alpha 1 minus 1, and V star equal to 1 by alpha 1 minus 1. And for feasibility of this U star positive and V star positive, hence alpha 1 bracket alpha 2 minus 1 by alpha 1 minus 1 is greater than 0, and 1 by alpha 1 minus 1 is greater than 0. Hence, alpha 1 minus 1 obviously positive, that is this positive quantity, obviously alpha 1 is greater than 1. Alpha 1 greater than 1. And alpha 2 minus 1 by alpha 1 minus 1 is positive. So alpha 2 is greater than 1 by alpha 1 minus 1. And so alpha 1 alpha 2 by 1 plus alpha 1 alpha 2 greater than 1. So for feasibility of E2 equilibrium point, alpha 1 is positive, and alpha 1 is greater than 1, and alpha 1 alpha 2 by 1 plus alpha 2 is greater than 1 also. Now, stability analysis. Consider f a function of the right hand side of the non-dimensional equation 4, and g is the right hand side of the non-dimensional equation 5. Sorry, non-dimensional 4 and non-dimensional equation 6. This is called f, and this is called g function of u and v. Then we find del f del u, del f del v, del g del u, del g del v. Then Jacobian j equal to del f del u, del f del v, del g del u, del v, del g del v. So we get the Jacobian is this, and for stability state E1 0 comma alpha 2, we put u equal to 0 and v equal to alpha 2, and then we get this. And obviously the trace of this matrix is this plus this. So alpha 1 alpha 2 by 1 plus alpha 2 minus 2. This is called T. And determinant of this J equal to this into this minus this into this. So this is equal to 1 minus alpha 1 alpha 2 by 1 plus alpha 2. This delta C. The discriminant T square equal to minus 4 delta. So T square means this alpha 1 alpha 2 by 1 plus alpha 2 minus 2 whole square minus 4 into delta. And after simplification, we get this whole square, obviously positive quantity. If 1 is less than alpha 1 alpha 2 by 1 plus alpha 2, that is if 1 minus alpha 1 alpha 2 by 1 plus alpha 2 is less than 0, that is determinant of this J is less than 0, then obviously, so 0 alpha 2 is saddle point. Discriminant is here positive, and if 1 is greater than alpha 1 alpha 2 by 1 plus alpha 2, that is delta is positive, and T is negative, and then because this 1 minus this quantity is less, this quantity is 1 is less than this. So this quantity is so T is negative. So T is negative, then 0 alpha 2 is a saddle node. For steady state E2 is U star V star. So Jacobian J equal to this. So with value this V star equals to 1 by alpha 1 minus 1. So 1 by alpha 1 equal to V star by 1 plus V star. So alpha 1 V star by 1 plus V is equal to 1. So 1 minus 1 is 0. So this is 0. And this minus V star by 1 plus V star equals to 1 by alpha 1. And trace of J means this plus this. So obviously negative quantity, negative, and determinant is this into this minus this into this. So this quantity is positive. Obviously, trace is negative, determinant is positive, so obviously E2 is a stable node. Now we hear extra part of this question, null-Klein analysis for du d tau equal to 0, and when the horizontal velocity component is 0, when that is either equal to 0, v equal to 1 by alpha 1 minus 1. The direction of arrows on these lines are vertical. And v null Klein's dv dt d tau equal to 0, that is vertical velocity component is 0 on these null Klein's. So dv d tau equal to 0, we get u equal to this quantity. And for this curve, we get put v equal to this, u equal to this, and we get the null Klein's this horizontal velocity component is 0 on this line, u equal to 0, and line v equal to 1 by alpha minus 1 on this. And on this u null Klein's, u equal to 0, and the direction, to determine the direction dv dt d tau, we get this if alpha 2 greater than v is positive and this negative if alpha 2 less than v. So alpha 2 is greater than v, alpha 2 if this dv d tau is positive if v is less than alpha 2, then we put here that is 0 less than v less than alpha 2, less than v alpha 2 is this. So for this part we put here upside arrow, and on the line v equal to 1 by alpha 1 minus 1, this is the horizontal line, and dv d tau equals to positive if u star greater than u. This is the u star is greater than u. U star is greater than u. So when 0 less than u star, we put vertical upward arrow. So for this part, on this line, straight line, we put here upward direction vertical arrow, and for this part, downward arrow. And similarly, on this curve, this the v null Klein's, on this curve, this v by 1 plus v equal to 0, du d tau equal to this, and this du d tau is positive if v minus 1 by alpha minus 1 is greater than 0, that is if v greater than v star, and less than 0 if v less than v star. So we put here right sided arrow, horizontal arrow, and for this portion we put here left sided horizontal arrow. For this portion, so actually from this portion, this you study a stable node. From this picture, you study a stable node. Next question, consider the following model of bacterial growth in chemostat. dH dt capital T my equal to mu1 sh minus dH. dH dt equal to d bracket si minus s minus mu1 by y1 sh, where H is the biomass population density, S is the concentration of substrate nutrient, D is the dilution rate, positive quantity, mu1 positive is the growth constant biomass, capital Y1 positive quantity is the yield biomass, and Si positive quantity is the concentration of the substrate in reservoir. Using the substitution, x equals to h by y1 Si and y equal to s by Si and t equal to dt, so that the above model reduces to the dimensionless form dx dt equal to ax y minus x, dy dt equal to 1 minus y minus axy, where the constant a is to be determined by E. Find the equilibrium points and investigate their stabilities. Now we have the model equation 1 and equation 2 and non-dimensional quantities x, y and t, and after simplification using these quantities from 1 and 2 we get dimensionless form of this model dx dt equal to a xy minus x, where a equal to mu1 si by d, and equation 2 dy dt equal to 1 minus y minus axy 6. Thus we have dimensionless form of the given model dx dt equal to a xy minus x, dy dt equal to 1 minus y minus axy. The equilibrium point, we must have dx dt equal to 0, dy dt equal to 0. So from the first equation, x bracket ay minus 1 equal to 0. So either x equal to 0 or ay minus 1. When x equal to 0, from the second equation, we get y equal to 1. And when ay minus 1 equal to 0, that is y equal to 1 by a, from the second equation, x equal to 1 minus 1 by a. Thus, we have two equilibrium points are E1 and E2, that is 0, 1, and E2 equal to 1 minus 1 by a, 1 by a. And for feasibility of E2, we must have 1 minus 1 by a is positive, so a is greater than 1. For stability analysis of these equilibrium points, we assume f equal to ax y minus x, gxy equal to 1 minus y minus axy, and find the partial derivatives of these quantities. The Jacobian j equal to this, and for E1, this j at the point 0, 1, we get this. The lower triangular matrix, hence the eigenvalues are a minus 1 and minus 1. Both of these will be negative if a minus 1 is less than 0. If a minus 1 is less than 0, then both of these eigenvalues is negative. So E1 is a stable node. But in this case, E2 does not exist because for existence of E2, this a is greater than 1. A is greater than 1. So we are obviously a is less than 1 does not exist. And if a is greater than 1, if a is greater than 1, E1 is a saddle point. And for E2 of this, Jacobian j equal to this, trace of j is this minus a, negative quantity. The determinant of j is this a minus 1. And for feasibility of E2, a minus 1 is positive. So this determinant is positive quantity. So trace is negative, determinant is positive. Hence the equilibrium point E2 is a stable node. Thank you for watching this video lecture, Chemostat.